Hello everyone, I'm sorry I couldn't be there in person, so you'll have to make do with virtual Greg for the time being, but thank you all for your understanding and your patience. So last time we finished up talking about frequency distributions and introduced the concepts of the mode and the mean of the mode and the median of a distribution. And those are two measures of what we call central tendency, as I introduced last time. So today we're going to be learning more about the mode and the median, but before we get to that, I wanted to touch on something that I wasn't quite able to convey as well as I would have liked last time, namely the notion of why we can use smooth curves to show a population distribution, and why we can't do that for a sample. So typically what we have from a sample of data from relatively small number of observations, when we try and plot the relative frequency distribution, as I've shown here, we have to use fairly wide bins in order to make sure that they all get filled. In other words, in order to make sure that we get a kind of reasonably good picture of the relative frequency distribution that we've observed. Now, as we get more and more observations in our sample, in other words, a larger and larger sample size, we can make those bins smaller and smaller. We can make them have a finer and finer grain, while still allowing them all to be filled up in a reasonable way. Until eventually, we can imagine having something like an infinite sample size, or so large that it might as well be infinite. And at that point, we've basically gotten to the population, and the bins are so small at that scale that the plot ends up looking smooth. So we get this nice smooth bell curve instead of these nice jagged histograms that we would normally have to do when we were plotting a relative frequency distribution. So to go back to one of my favorite examples of dog pictures, it's sort of like starting from a very low resolution picture of the data where we have to take a fairly coarse grain, and as we get more and more observations, we can pick out more and more of the small scale structure in the data until eventually it might as well be a nice smooth curve, and we've basically gotten a picture of the population and not just of our sample. And I'll take this point to point out for you that in this way, so I've mentioned that a particular statistic is often considered as an estimate of a population parameter. So a statistic that's derived from a sample can serve as an estimate of an unknown population parameter. And in this way, we can think of this smooth distribution shape as being like the unknown population parameter relating to the frequency distribution, and something like we have over on the left, where we have this kind of jagged histogram, represents an estimate, admittedly imperfect, but an estimate of that smooth frequency distribution of the population. And as you can see, when we have more and more observations, larger and larger sample size, that estimate gets closer and closer to the smooth population that we have on the right. So I just wanted to take this time, like I said, I hope to help clear up any potential confusion about the notion of using a smooth curve to plot a population distribution. And with that, we are ready to move on to our set of examples for the day, where we'll be learning about the mode and the median. So before we start talking about the nitty-gritty of modes and medians, I thought it would be good to go over once again why we're even computing these numbers, why we even care about these sorts of things. In other words, why do we even want a measure of central tendency? Well, often what we need to do is know what values of a measured variable are typical or expected sorts of values, values that are representative of the kinds of data that we tend to see. And to go back to the set of questions I talked about the very first class, the estimate of central tendency is often an answer to the question, if you had to guess, which outcome would you think will happen? And as well, it's kind of a useful way of summarizing a set of data in terms of its typical behavior. So rather than conveying every single value in the data set, we can just tell people a single value that is somewhat representative of the entire set of observed values. That's what we want from a good measure of central tendency. And our set of examples for today, you probably thought I was going to use football-related examples, but I'm not a huge football fan, I admit, although I did catch the very last, like the end of 10 minutes or so of the game last night. It was pretty good. But what I at least used to do back when I was in better shape was do a lot of running of stupid amounts of distances. So including this one, the Virgil Crest Ultra Marathon, which sadly is no longer in existence. They've converted this mountain from being one suitable for running to one where you can just tear it up with your mountain bike, I guess, if you want. But at any rate, the idea is that you run, quote unquote, up and down a mountain near Cortland, and they have a couple of different courses that they do. They have the 25-kilometer one. I did the shorter one. I'm not this crazy. They have a 100-mile one, which I've bet some people have done, and they are as crazy as you would think. But we're going to be looking instead at data from the 2015 running of the 50-mile course. So research question number one that we might ask is, where do people come from who are stupid enough to do this? So I will ask you now, since of course I can't call on you, although, well, that would be quite a feat. What kind of research is this? So I will take this time, pause, let you think about it, think real hard. I'm not going to give away the answer, but I suspect you can figure it out. So is this descriptive? Is this correlational? Is this experimental research? Well, you can think of that on your own. In any event, the data that we have to work from in this case is the state of origin for each finisher of the 2015 running of the 50-mile course at Virgil Crest. And here we see here, it should be pretty clear that there's a number of New York entrants, as you would expect, but it seems like there's a fair amount of variability there as well. So again, I will ask you a question, but not answer it. What kind of data is this? Is this on an ordinal scale? Is this on an interval scale? Is this on a ratio scale? Or is this on our old friend the nominal scale? Well, think about that, and we'll move on to our next question. So we have in this group here, we have 60 observations. There are 60 people that finished the 50-mile course. And again, just to keep this sort of in your heads, when would we consider this set of observations here to be a sample versus when we would consider it a population? So for this one, I'll expound a little bit more. So we would consider it a sample if the 2015 running was meant to be representative of, say, all Virgil Crest runs or all ultra marathons around 50 miles, something like that. But we might also just be concerned with this particular group of people, in which case this would constitute our population. There's no sense in which we're trying to use this to generalize to anything else. We're just trying to describe this group. And for the purposes of today, we're really only going to be thinking about our data is coming from a population. We're not necessarily trying to generalize too much, but nonetheless, these are an illustration of how the same set of data can, through a different lens, depending on the kind of question you're asking, be considered either a population unto itself or a sample that is meant to be representative of a larger population. So, based on what we did last week, we can take our set of observations here and do some fun things. We can make our frequency distribution table. Not too complicated here. Here the states are just organized alphabetically. But a hint to the question I asked earlier, there's not really any meaningful order to these different states. The alphabetical ordering was purely arbitrary. But nonetheless, we can see there's mostly small numbers. Big one at New York. We can do the same thing, and you take the same data and make a bar chart with the height of each bar corresponding to the frequency with which each state is observed. And it's pretty clear from all of this that New York is the mode of the distribution. That is to say, most people in the sample come from the state of New York. Now, we've talked about the mode before. It's a fairly simple idea. It's just the most frequently observed value in our data set, which value occurred most often. But as we'll see, it doesn't say anything about how often other values were observed. So the mode, seems like a good thing to know, but maybe it's not the most typical. So we usually apply it to nominal or ordinal data because those are things where we have very clear, discrete observations that kind of can't blend together in any way. But it can also be determined for interval or ratio data if we're using a grouped frequency distribution, which we'll see an example of later on. So, going back to our research question, this was the original data we had, where we had a whole lot of people from New York, some people from a couple of other states. New Jersey and Pennsylvania kind of seemed to be the runners-up, and then it's a smattering of other things. But what if we had a whole lot of Pennsylvanians? So we had 32 people from New York. What if we had 31 people from Pennsylvania? Or what if nobody from Massachusetts had shown up? Or what if a bunch of people from a bunch of other random states had shown up? Well, it should be clear that the mode, New York, remains the same in any of these scenarios. So this is what I mean when I said the mode only tells you the most frequent value. It doesn't tell you, for instance, how close the next runner-up is, and it doesn't tell you how many other values may have been observed. All it tells you is what was the most frequent. So, moving on to another research question, one that's perhaps more germane to the question of running a race. How quickly do people tend to finish? So one of the funny things about ultra marathons is that you're not, unless you are extremely good, you're not generally running it to achieve a certain like at like a 7-minute mile, something like that. That you just can't sustain that for that amount of time. So the finishing times that tend to be, I guess, somewhat more distributed, somewhat more variable than you would get in a typical kind of race. So the data in this case are just the time to finish for each finisher measured in hours. So the fastest person, so this is in order, so the fastest person in this case finished the 50 miles in a little over 8 hours, so fun way to spend your day. The slowest person still did it in 17 hours, just shy of 18, which is still quite respectable when you consider that you're going up and down a mountain and you're doing it for 50 miles. So, at any rate, yeah, this is I would say, fairly typical of if we were thinking of this as a sample rather than as a population. I would say this is a pretty representative sample of 50-mile ultramarathon finishing times. But to keep up my trend of asking questions that I can't actually directly get answers from you, I will ask, what kind of data is this? So this is a time. It can't be any less than 0. That's a major hint. And it could be anything greater than 0. So, I mean, yeah, assuming that someone finished the race. So, you could have 13 hours, you could have 13 hours and 1 minute, you could have 13 hours and 2 minutes, you could have any value in between. So, given all those hints, you should be able to figure out and infer what kind of scale these data lie on. Now, we can do what we've been doing, make ourselves a nice little frequency distribution plot. In this case, this is a histogram based on grouped frequency, group frequency distribution. So here, the width of the class intervals, I just arbitrarily set it to 1 hour. That seemed pretty good. And so we can see that, well, 14 to 15 hours, this bar here, is the modal finishing time interval. That is to say, the most finishers ended up finishing between 14 and 15 hours. So, yeah, that's all right. That's it is what it is. But is that really the best guess that we could make about how long someone would take to finish? So, just to point out a couple of features of this data. So, okay, 14, 15 hours does seem to be, well, it's clearly the most common, but it's not that much more common than 13 to 14 hours. And there's actually a whole lot of people down here who finished between 8 and 13 hours. But you would have no way of knowing that if all you knew was the mode. If all you knew was that people took, or most people took 14 to 15 hours to finish. Well, I say most, but really it's 13 out of 60, so that's about, remember our proportions, so 13 divided by 60, that's a proportion of 0.22, or a percentage of 22% who finished in that interval. So it's not really the majority, it's only a plurality of people that fall into this category. So again, maybe the mode is not the most informative value to give someone if you wanted to know how long people tended to take in this kind of race. In addition, we might have a situation where we have a bimodal distribution. So this is something I talked about last time, and it's a distribution where there are 2 peaks. Now, of course, you can also have 3 peaks. You could have a trimodal distribution, and so forth. In general, we call these things multimodal distributions. And as I talked about last time, a multimodal distribution, in this case maybe a bimodal distribution, tends to happen when you've got a 2 groups of people that you're kind of smearing together into one. So 2 groups that you should have treated separately, but which for whatever reason you've lumped together. And here in the blue dashed lines, I've just kind of guessed at what sorts of distributions of finishing times might characterize each subgroup. So we might have a kind of slower group that tends to peak around 14 hours, and then a faster group that tends to peak between 10 and 11 hours. So given that there are potentially these 2 modes, we would call the bigger one the major mode, so 14 to 15 hours, that interval, we consider that the major mode, and then the minor mode is the somewhat smaller one, which is 10 to 11 hours. So now, I will say this is not perfect. It's still a finite data set, so is it better to think of this as having two modes, or maybe it's just a very negatively skewed distribution? This one I leave up to you to figure out which seems like the better description. Now, a negatively skewed distribution seems plausible. At the same time, so we'll see a little bit more data from this race in the next class that will maybe start to convince you that there really is a bimodal distribution, which is to say a group of people that is somewhat faster and a group of people that kind of closer together that are somewhat slower. This would be me in the slow group, that is to say. But that there are really two different kinds of people who do this kind of race. So, but that's for next time. So, given though that we're having a lot of trouble just even necessarily picking out a mode of this distribution, maybe we should look elsewhere for something that could be a better description of the central tendency of this distribution of finishing times for the Virgil Crest race. So one such count that we might give is called the median. And again, we talked about this last time, where while the mode tells us the most common score, it's tricky that if there's no clear winner, what do we do? And also, in general, for interval or ratio data, we can only find modal intervals, not particular values. So again, we're kind of stuck in the situation of, well, what if we had decided on values with, intervals of larger width or smaller width? Well, what do we do then? So the median doesn't suffer from these problems, although it still has some other things going on with it that we'll talk about in a bit. But what the median tells us is the midpoint of the distribution. So specifically, half of the observations are below the median, half of the observations are above the median. And as I described last time, that means that the median value is equivalent to the 50th percentile. So it's the thing that divides the distribution into two equal halves. That's how the median is kind of conceived. So just to illustrate this more concretely, imagine that we had only observed these finishing times, this set of 5 finishing times here. So to find the median, as I described last time, you first have to put the observations in order, which they already are here. Very nice, very convenient. And then half of it would be the stuff up here, and half would be down here. So the value that divides it into two equal halves, the median, is 8.75. You see, the lower half has 2 observations in it, the upper half has 2 observations in it, and so we found the median of our data set. So that's the case when you have an odd number of observations. When you have an even number, as I described last time, you have to do a little bit of computation, because once again, we want to find a value that puts an equal number of things into the bottom half as the top half. So we've got 3 things in the bottom half this time, 3 things in the top half, and the value that we want, though, is somewhere in between. It's neither 8.75 nor 9.35. It's somewhere in there. So in practice, we don't necessarily, any number between those two values could technically count as the median, but as a rule of thumb, what we do is just take the value that's halfway between those two middle values. So we say 8.75 plus 9.35 divided by 2, and we've got our median. It is 9.05, which seems like a fair way of dividing the data that we have into two equal sized groups. A lower group down here and an upper group up there. So to go now to our full data set, how quickly do people finish the race? What is the median finishing time? So once again, we start by putting all of our data in order, from smallest up here to largest up here. Divide it into two equal halves. So remember, there are 60 total observations, so that means there's going to be 60 divided by 2 equals 30 observations in the bottom half. That's in the kind of light gray background, and 30 observations in the top half, and that's in this kind of dark gray background. And the median is going to be a number that is between, well, luckily, and again, this was just chance, it turns out we had two people that actually finish at about the same time. Whether they finished at exactly the same time, I couldn't tell you. This is an issue of real limits. Our measurement scale doesn't allow us to tell whether these two people actually finished at exactly the same time or just at very similar times. Nonetheless, 13.15 hours, so we can mechanically go through our computation, do 13.15 plus 13.15 divided by 2, and we get 13.15 out as our estimate of the median. And what we can do then is kind of indicate using this grouped frequency distribution here, the histogram, the median would fall roughly there. So here's the kind of bottom half of the data, the fastest finishing times, and here are the upper half, the slowest finishing times. And here, and slightly, slight abuse of the x-axis, the 13.15 would be somewhere around there. And so, an interesting thing that we've gotten out of this median is that it actually does seem to mark a divide between a fast group and a slow group. And it seemed, but again, I'll throw to you a question. Not sure if there's a right or wrong answer here. Does this seem like a good guess about how long someone might take to finish the race? Well, I will give you some arguments in favor of this as being a good guess about how long someone might take to finish, in that, well, if you don't know if someone is going to be in the fast group down here or the slow group up here, so imagine you didn't know anything about the person other than that they, for whatever reason, were stupid enough to run the 50-mile Virgil Crest course. Well, if you didn't know which of these kind of two modes the person belonged to, you might want to guess a number that was somewhere in between, right? It's kind of hedge your bets. Well, the median seems to actually do a pretty good job of that, of kind of falling in between these potential modes for a fast runner versus a slow runner. So, 13.15, maybe not the worst guess you could give. But the median still has some issues, just like the mode. So imagine that instead of being just shy of 18 hours, the longest time was over a day, 24.6 hours. And I will say that most of the people that do the 100 miles do take about a day to actually finish that. And you can imagine for yourselves what kind of experience that is. So imagine that we had changed this value. So now it's a huge number, wildly off from anything else that we'd observed. Well, as you can tell, the median is still the same place where it was. It doesn't really matter if this value is 100 or 1,000. the median is still going to be right there because it just cares about the total number of observations, not necessarily what those observations actually were. So just to plot again kind of what this looks like in terms of frequency distribution. So here I've replotted this with our very, very slow runner out here, and the median has now moved, has not moved at all. It's still at 13.15, but it's clear that there's this pretty big gap here, and the median isn't telling you anything about that. So, once again, just like with the mode, the median is not necessarily the most sensitive measure when it comes to describing typical values of the distribution. But to put it on the other side, maybe a finishing time of 24.6 hours is not typical and is not representative of most people's finishing times, and as such, maybe it really shouldn't impact your measure of central tendency. Maybe you really shouldn't care about this one guy who's really far out. You should just care about this kind of central group that all has finishing times that are reasonably close to one another. So, like I said, there's not always a hard or fast answer to this, but I hope that I've incited some thought in your head about whether this is a good estimate of the central tendency for this kind of distribution. So just to review, the median is the value that divides a distribution into two equal-sized parts, and I want to emphasize that it can be useful both as a measure of central tendency, which is our focus now, and as you could see from this example, it's potentially useful as a way of splitting up observations into groups in case you discover that there are, may in fact be multiple modes to your distribution. So the median is often a good way of splitting up groups of that nature. But like the mode, it's not always sensitive to changes in the data. Now we can take what we've seen about the mode and the median and directly compare the two. So first, at the level of the definition of each term, the mode is once again the most common observed value, whereas the median is the value that divides our observations into two equal halves. It splits the data set in half. The mode is applicable to nominal and ordinal scales, but also to interval and ratio scales when using grouped frequency distributions. The median, on the other hand, can be applicable to ordinal data in some cases, but is often used for interval or ratio scales, but can't be used for nominal scales. Now, I throw the question to you as to why you can't compute a median for a nominal variable. And to help you discover the answer, I will point out that for a nominal variable, there's no way to place the values in any fixed order. So there's no way to say whether one is bigger than the other. So that should give you a clue about why the median cannot be computed for nominal variables. All right. Now, like the mode, the median is once again insensitive to many seemingly drastic changes in the data. And you can think of the mode as basically only seeing the most common value. It's as if the other ones just didn't matter at all when it comes to the mode. And similarly, the median only sees the midpoint. The median only tells you where that midpoint is, not necessarily how things are spread around outside of that midpoint. So this is pointing to the need, perhaps, for a different measure of central tendency, which we're going to call the mean. And the mean takes into account all of the data. It gets to see every single observed value, and all of them influence the mean. So, all right, that seems good, right? If you want to summarize a set of data, surely you'd want to use a measure that actually incorporates every single observation into the computation. Well, maybe that's not a good thing. Like I showed in the example of the exceptionally long race time, maybe there are values that are in your data set that shouldn't inform your measure of central tendency. So this may not be a good thing, but sometimes it is. So next time, in addition to talking about the mean, we will directly compare the mean, median, and mode, and kind of go over some rules of thumb for where each of these measures is most suitable for the data at hand. So once again, I want to thank all of you for putting up with virtual Greg for the time being. I really do appreciate it, and I apologize for the inconvenience of this, but my thanks to you for dealing with it, and I hope to see you all on Wednesday, assuming that all these things get worked out. So thanks again, and be seeing you.